Okay, so to finish the story of this new partial derivative thing, let's, I'll go through question 2b from the applied calculus recitation. We've got our trapezoidal roof gutter. With sides of some length, let's call it x, and that are bent some angle theta or phi or whatever symbol you'd like to use. There's a couple things we need to know. We need to know that the area of a trapezoid, which is the cross-sectional area that, if we looked at this, this is end on, but this is a cavity associated with the length of this sheet of metal. We know the width, we don't know the length. Assume it goes, deep into the whiteboard. But that's kind of irrelevant to our purposes. We need to know what's the size of this cross-sectional area, because then we can just multiply by the length of the thing, whatever it is, and that gets us our biggest volume. So the area of a trapezoid is 1/2 times the altitude times the sum of the two bases, or actually it's the height times the average of the two bases. Okay, so we know one of the bases in terms of x, this short one here, because this whole strip of metal is 9 centimeters wide. So we know that base 1, let's say, is the whole 9 centimeters minus 2x. The second base is that same distance plus those two horizontal sections on either side. And those two horizontal sections on either side we can find with the Pythagorean theorem, I think, or maybe with right triangle trig even. So if we talk about this and call that A, then if we think about, that's also this distance, and that would be x cosine theta. So then the second base is the first one plus these two legs of right triangles. Base 1, base 2, we also need h in terms of the two variables of interest, x and theta. But I think that's the other trig function. Okay, so now we can write area as a two variable function of x and theta. Um, okay. So we've got 9 minus 2x plus another 9 minus 2x. But we've got this factor of a half out here, so we can distribute that. We also have 2x cosine theta, but with a factor of a half if we distribute just x. X sine theta 9 minus 2x plus x cosine theta. Nine x sine theta. If we distribute these two terms are linear in x, so I'm going to combine them. So that when we distribute through, we only have two terms. 9x sine theta and cosine theta minus 2 x squared sine theta. Okay. So now we need to involve the partial derivatives. In order to be a maximum cross-sectional area, it has to be a maximum with respect to theta and with respect to x at the same time. Because if it isn't, then the area has room to increase along whichever one it isn't a maximum for. So let's take the partial derivative with respect to theta and the partial derivative with respect to x and set both equal to 0. Partial with respect to x. Hold theta constant. That just looks like constant times x. So we get the constant from the derivative. Cosine theta minus 2 times sine theta. That's all held constant. The only thing we've got is x squared, 2x. Times all that stuff that's constant. Cosine theta minus 2. Partial derivative with respect to y, or not y, theta. Now we're holding x constant. So that's 9x times the derivative of sine, which is cosine. Here, we're going to need the product rule because this is a product of two trig functions of theta. X squared is our constant. We can keep that out front of the product rule. The first times the derivative of the second plus the second times the derivative of the first. 2 is a constant with respect to theta, so when it becomes 0 in the parentheses there. Let's set both partial derivatives equal to 0. And then let's solve. Both of these terms have a sine theta. We could factor it out and divide by it as long as it isn't 0. Sine theta would be 0 only if we leave it flat, which wouldn't get us any carrying capacity at all. So because sine theta isn't 0, nine plus 2x cosine minus 2 is 0. All right. We have two options. We can either solve this equation for x and plug the result in here, because remember, both equations, both partial derivatives need simultaneously to be 0 in order for what we're finding to be an actual maximum of the cross-sectional area. So we've got a system of simultaneous equations. So if we solve one for one variable, we could plug that into the other. We can either solve for x or theta or cosine theta, and that's, I know from experience that trigonometric equations are often tricky to solve for theta, for the argument of the trig functions. So if I can eliminate it and express it in terms of x, I'm happier. I'm not sure yet if I'm going to be able to do that, but this thing here in square brackets makes me think that there is some simplification I could do before I try to solve the system of equations. 9x cosine theta plus x squared. So let's distribute. This is cosine squared minus 2 cosine minus sine squared. Now, sine squared theta, if we think about Pythagorean identities, sine squared plus cosine squared should be 1. So sine, we could replace. Sine squared, we could replace with 1 minus cosine squared. All right, minus 1 minus the minus gets us plus. So we have cosine squared. So we've got 2 cosine squareds. So if I could replace cosine theta with an expression in terms of x, then I've got an equation I can solve for x. Subtract the 9, divide by 2x, add 2. I'm going to have to square that. I don't want to have all those terms. What if common denominator? What if we write it as one fraction? Then we can just square the top and bottom. That would be 2. Yeah. The common denominator is 2x. We had a 2. Yeah. Okay. So that's cosine theta. I'm on a whiteboard, so I'm going to have to erase a little bit, but I'm working with this equation, plugging it into this equation. Got to square the denominator too. Okay, that's kind of messy looking, but it's going to simplify. We've got x over x. So we can distribute the 9. The 2 and the 4 will partially cancel. We'll be left with a 2. If we distribute the x squared will cancel this x squared. So we'll just have the numerator. I'm going to FOIL that out. 16x squared minus 36 is 72x plus 81 all over 2. Here, the 2's fully cancel. And one of those x's is going to cancel. So we just have to distribute an x into 4x minus 9. X squared it's not bad. It's a quadratic equation in x. This is reasonable. We can solve this. Distribute the minus sign. Minus 4x plus 9x. And I'm thinking to divide the 2 up through. We've got 18 minus 81 over 2 plus 81 over 2. Those 81s over 2 are going to cancel. Eight minus 4 minus 1 gets us 3. x squareds, 18, well, 36, 18 plus 9 is 27, minus 36 is negative 9. That's it. Let's factor out the x, because if x is 0, then we haven't bent up the sides at all, and again, it's a flat line. So 3x minus 9 equals 0. Or x equals 3. Okay. So let's plug 3 back into this equation. Well, minus 9 over 6 is 1/2. And that means the cosine if cosine is 1/2, then it's 60 degrees. So we've leveraged the partial dependence of the area on both the size of the sides and the angle to which we bend them to determine that the sides should each be 3 centimeters out of 9, and that we should bend them 60 degrees. Again, there's not too much sort of fundamentally that's different about this than our sort of traditional single valued optimization problem. It's just there are multiple pieces. And we treat the dependence of the variable of interest on each piece and solve the system simultaneously.